So this is especially useful, potentially useful if you're going to do some sort of percent damage or overlap or regional analysis. But also, because the AAL atlas comes with a set of labels, it tells you what region this is. So it looks like the left superior frontal gyrus. And by the way, I should mention that all these programs are under active development to some extent. I tend to add features when I or someone I'm working with needs them. But I also add features when somebody that I just want to help needs them. And if there's something that doesn't work the way you think it should, or that doesn't have a feature that you think would be especially helpful, please let me know, because the goal of designing the software and writing it is to make lesion analysis as easy as possible, while also making it as correct as possible. Another useful command, and this is one that I want to emphasize. Well, I'm emphasizing them all, but I'm going to emphasize this one now. It's called Vbim, which stands for Vbim's Compare, which is a shorthand for saying it's a general-purpose image Swiss Army knife kind of program. And all of the voxel commands that don't have a graphical interface, you can type the name of the command all by itself and get a help screen. So here's all the help from Vbim Compare, and what you'll see right away is that it actually, there's actually so many different options that it scrolled off the screen many times over. So this tells you a few things. One is that this program has a lot of options. Two, that I'm not really good at designing help screens. But nonetheless, you can usually find what you need in here. So it has lots of things like thresholding, smoothing, adding constants, adding images together, different kinds of arithmetic, mask operations, byte swapping, zeroing out the left or right side of the image, masking in and out various regions, thresholding, averaging, and of course at the end writing out the image. So what you can do with this is lots of different stuff, because all these operators can be combined, can be applied in series to images. So here's one example. I'm saying Vbim lesions.test.gz, which is our lesions file. I'm giving it the count operator, which means basically replace all the image data with a single 3D image of how many patients or lesions in each voxel, and then write it out to this file. Okay, so I've done two operators, and one of them was the output operator. That's not that exciting. But here's one that's slightly more exciting, if trivial. Here, I'm taking the lesions file. I'm saying include 0, which means basically throw away all the data except for the first volume. I'm converting it to a more compact data format. I'm multiplying the whole image by 0, and I'm writing it out to a file called mask1. And you may wonder why I would multiply an image by 0 and then save it. It's because I'm going to use it for the next command as a blank mask. So obviously there are more exciting things you can do when you have all those arithmetic and image processing operations at your disposal, and many of them do come in handy. For example, one thing that I should have done here but didn't is, after counting, I could have said -thresh 4.5, and that would throw away all voxels that have fewer than 4.5 lesions. I usually do 4.5 instead of 4 or 5 because I can never remember if it's less than or less than or equal to 7. It's a good hedge. So Voxel also has an image viewer. In many respects, it's similar to MRIcron. In many respects, it's different. What I'm going to do here is load up the column brain. I'm going to load overlay as a stat map, that count map that I just created, and I'm going to overlay as a mask that mask that I just created. Okay, so let me just turn off these volumes. One thing you can see right away is that the mask has nothing in it. At least not on this slice. Of course, it has nothing on it anywhere because you all saw me set it to 0. Here's the count map, which by contrast has data everywhere, just about everywhere in the left hemisphere, really frequently. And some of these voxels were lesioned in as many as, I just saw 42. There may be higher numbers somewhere, probably not too much higher. And they go down to 1. And then where it's 0, you don't see any color. We could, if we wanted to, set a threshold at 20 to only see really frequently lesioned voxels. And we could load other stat maps on top of this and overlay them translucently. They're all translucent. There are math drawing functions in here. I don't necessarily recommend that you use them if you prefer to use Neuroicron, but they do work. And I just want to draw a mask real quickly because I have a reason to. Start visible. Let me set the radius to less than. Okay. So I'm going to create a little mask that looks like that. I'm going to save it. I'll save it over that mask one that I created. And now I'm just going to add a little more. And I'm going to save that as mask 2. Okay. So my goal in showing this to you is not to just show you that VBView 2 can also draw masks, but it's actually helpful for demonstrating the next tool program I'd like to show you.
Does Voxel use radiological convention?
Voxel will display your image in the sort of order of bytes in the file. So if the file's x-axis goes from left to right, then it'll show you a neurological convention. If the file's x-axis, so basically if the first byte in the file is left hemisphere, then it's neurological. If the first byte in the file is right hemisphere, it's radiological. Some programs now that use Nifty format will actually pay attention to Nifty's orientation information and flip the file if it indicates that left is left or right is right or left is right. They'll flip it when appropriate. At some point, Voxel might make that an option. At this point, I find it actually very difficult to keep track of which program is doing what in which version, and I think it's most helpful to sort of have some other way of verifying that the images you're looking at have the orientation you think. But for right now, Voxel just shows you the images in the order they're stored in the file. Oh yes, this is my note to myself to draw those two maps. I did. One thing that you can do, another useful command is Vbcmp, which will compare any two image files. So I can compare those two image files that I just drew, and it tells me that of the 7 million or so voxels, 249 of them were different between the two volumes, and of those 249 that differed, the mean difference is 1. So this turns out to be a surprisingly useful thing to have for various reasons. One reason is because sometimes you just need to compare images because you want to see just how different they are. Are they meaningfully different, substantively different, or are they just, strictly numerically different, but not actually different in any meaningful way? The other thing is sometimes you can't remember if you've done something or not. So you may think that mask 1 in one directory, mask 2 in another directory should be identical, but you may not remember if you actually did something to it or drew another voxel. So this is a useful way to tell. And one thing that I really encourage when you're doing image analysis is constantly double checking on everything you're doing, and when possible doing things more than one way, because it's very easy to get disoriented with image data, no matter how long you've been doing it. You're frequently managing lots of different files, lots of different dimensions, and lots of different processing streams, some of which may be interrupted partway through, and so on. So repeating analyses and trying analyses different ways and making sure that they can be repeated easily is especially important.
Different voxels here refers to different lesion patterns in the voxel? Or
no, these are 3D volumes. This is just basically saying these two 3D volumes have 249 voxels that don't have the same value. It's that extra blob that I drew. Yeah. So these down here are the 249 extra voxels that. And in fact, if we loaded mask 2 as a stat map, we could do the same thing here. So now I've loaded mask 2. Let me turn these other ones off. Set the threshold to 0 because those values are all 1. I'm going to click here, and I'm going to say, I'm going to say find the region of crosshairs. Okay, so now it's just found that unique region, and now I can do control I and get some information about that region. And indeed, it has 249 voxels. The sum of which is also 249 because they also all have the value 1. And you can see the center of the peak, the minimum value, the maximum value, and so on. It's not really that useful for masks. This feature is more useful for stat maps. The other way you can compare two masks, which is particularly helpful with lesion analysis, is something called Vbms Compare. Okay. So same two volumes. I'm comparing the two volumes, and this gives you a bunch of different ways of looking at the differences between these two volumes. So mask 1 has 365 total voxels. Mask 2 has 614. I hope the difference is 249. I'm not sure. Mask 1 has no unique voxels. Mask 2 has 249 unique voxels. Right here. The total union of the two is 614. I probably could have come up with a less trivial example. The intersection is 365, which is exactly the size of mask 1. The dice overlap coefficient is 0.7457, and so on. Some other measures of the differences and discrepancies between the two boxes. So this does turn out to be useful occasionally in lesion analysis if you want to get measures for, on average, how similar lesions are in a group. But especially if you're doing something like inter-rater reliability, and you want a metric of how similar two raters' drawings are of the same lesion. So that's just a little selection of the 100 and some commands in Voxel. I'm not going to say that those are always the most useful. There are times when I mean, obviously, all those programs are there for some reason or another, and I think that these are the ones that I tend to go to the most often for lesion analysis related stuff, aside from the statistical analysis ones, which we'll talk about in 2 weeks. Does anybody have any questions about all that? It's all kind of fairly trivial, and it's mostly covered on the cheat sheet. But so I should also mention that one thing that was not obvious because I didn't have a diversity of files in that directory is that for the most part, the data you'll see in association with image analysis comes in four flavors: one-dimensional, two-dimensional, three-dimensional, and four-dimensional things. 3D files tend to be brain volumes. 4D files tend to be series of brain volumes, like a series of lesions or fMRI time series. 1D files tend to be vectors that have things like behavioral scores or other variables used in your analysis. And 2D files tend to have matrices, although you can also have 2D images. Often 2D images are stored as 3D volumes that have the third dimension that happens to have a value 1. So VBI does understand a lot of different formats for all of those. Voxel in general understands maybe a half dozen different image formats, and so all these programs will work with analyze format, nifty format, vox-based formats, DICOM format. It doesn't really care. Everyone's software has its own idiosyncratic set of formats that it understands. We tried to add the most common one to Voxel. It also understands Gordon's ROI format if you have that other file in there. There are a few others. And the other thing to know about these commands is that when you are specifying an output file, it's smart enough to know to sort of guess what you want. So if I say VBconv, this is Voxel's little conversion program, mask1.nii.gz to foo.cub, it's going to create an uncompressed cub file, which is Voxel's 3D format. If I run the same command that say foo.cub.gz, it gives me a compressed cub file. Or if I say foo.nii, it's just creating a nifty file, and so on. We've never added DICOM output to Voxel because nobody ever asks for it. At least nobody has yet. So the last thing I'd like to talk about before I hand this over to Hoon is what I'm calling concepts in image space. And I just want to go over this briefly because I think most of these are pretty intuitive, and I imagine that most of you understand these at some level. But since these terms come up over and over in doing lesion, doing all kinds of image analysis, I just want to go over these.